So in grade 10, you were introduced to various topics or various concepts. So one of those concepts, especially with respect to quantitative aspects of chemical change, was the molar mass, concentration, as well as molar value. I think you did this molar value in grade 11, I might be mistaken. But by grade 12, you should be able to be quite familiar with the equations that I'm going to show you just now. So let's just get started with it and say, how do we then define a mole? So a mole basically is just one. Why am I saying one? A mole is basically the SI unit for the amount of substance. So when we speak about a mole, we are actually just saying the amount of a substance. And there's an interesting thing where 1 mole of a substance equals to 6.02 multiplied by 10 to the power of 23 particles. So this can either be ions or atoms. So a mole of particle is an amount of 6.02 multiplied by 10 to the power of 23 particles. And I'm sure you already recognize this number. This is what we commonly refer to as Avogadro's number. So do you write Avogadro's number or Avogadro's constant, depending on whichever one you use? And we normally say it is Na, and we say it is equals to 6.02 multiplied by 10 to the power of 23. So there's an equation that you should be familiar with where we say, okay, if you wanted to determine the number of moles in a substance, and we knew the number of particles n, and we also know this value Na. Through this calculation, you can actually determine the number of moles. But then why do we use moles instead of just using this very big number? So the thing is, in a maybe a solid or a certain substance, there are way too many particles in there to count. So this is the number of particles, ions. It can either be ions or atoms, or and then this is Avogadro's number. You know Avogadro's number. And then this is measured in moles, as we know. Mole. So N is the number of moles. As I was saying, there's way too many particles in a substance, such that at least when we use the number of moles, we can just our calculations become easier instead of just using these huge numbers. It's even impossible to count the total number of ions or particles in a specific substance. So we use the number of moles, right? Okay, so please I'll be able to use this equation. Like I said, if you were given the number of particles or the number of ions, and you were asked to calculate the number of moles, we would just say it's the number of particles divided by Avogadro's constant or Avogadro's number, right? Cool. The second thing that you ought to know at your level, or at least the second equation that you need to be able to use at your level, is when we talk about molar mass. So you should be able to calculate the molar mass of compounds or molecules or whatever you name it. So, and molar mass can be related to the number of moles through this equation that I'm sure you are quite familiar with, right? So N still is the number of moles measured in moles. And then M is your mass of the whatever substance, it's measured in grams. So this is your mass, and here it's your molar mass, and your molar mass is measured in grams per mole. So let's say you're given the mass of a particular substance, and you also know its molar mass, then you are able to also calculate the number of moles. So the mass in grams of 1 mole of a substance is measured in grams per mole, and this is what we call the molar mass M. Hopefully you guys know how to actually determine the molar mass of all your elements in your periodic table, or when you give in a compound, you should be able to know how to do that by now. And the third thing that I wanted to talk about is concentration. So remember the equation that we are familiar with for concentration is C equals to N over V, where this is the concentration and it's given in mole cubic decimeters, right? And then here N still it's the number of moles, it's measured in mole, and then volume again is cubic decimeters. So the important thing here is always make sure that these values are the volume value. If it's not given in decimeter, in cubic decimeters, you convert it to cubic decimeters. So you should also be able to know how to do something like that. I'm not going to be doing the calculations because these are quite basic stuff that you should be able to know. And then in the upcoming lesson, we're just going to use them and you will see how and when we can use them. But you can also rewrite this equation over here. Let me find another marker. Because remember, we already know the equation for, what is this thing? So we already know the equation for the number of mole, and we said it's m over m, right? So meaning we can just substitute this n value right there at the top. And when we do that, you find that the concentration is nothing but m over m, so this is big M, all of it divided by V, which will give me something like this. If you work it out and you do the mathematics there, you're supposed to come to a value of mv. So this is small letter m for mass, this is big letter M for molar mass, right? So let me see if I have left something important in terms of concentration. So like I said, so concentration basically refers to the number of moles per unit volume of solutions, right? And then yeah, concentration. So it means that the concentration is the number of moles of solute per one deci per one deci per one cubic decimeter of a solution. So if we given, what do I mean by that? So if we given a concentration and they say it's why am I writing square? It's 1 cubic decimeters. So what that is telling you that it is that for every 1 cubic decimeter, so for every volume of 1 cubic decimeter, there is 1 mole. I hope that is making sense, right? So I want us to kind of move our discussion to something that is also very important. And please note that I'm just kind of touching the surface right now. I'm not going into deeper details about this because you did this in grade 10 and grade 11. And in the next few lessons, when you do stoichiometry and all of these calculations, I'm going to assume that you guys are able to actually work with these equations. So there's also another thing that we can describe. This actually looks dirtier now than it did before. There's also another thing that we can describe, and that is called the molar volume of a gas. Molar volume of a gas. And let's say we call that Vm, right? And then at STP. Sure, everyone is familiar with this. So this is standard temperature and pressure. And they say that Vm for all gases at STP, that's important, is equals to 22.4 cubic decimeters per mole. So for all gases at STP, the molar volume is 22.4 cubic decimeters per mole, right? So what does that mean actually? This means that at standard temperature, so remember our standard temperature is 273 kelvins, if I'm not mistaken, or if you write it in degrees Celsius, it is just at 0 degrees. And our standard pressure is 1,013 multiplied by 10 to the power of 5 pascals. So at this temperature as well as at this pressure, the volume of all gases is 22.43 cubic decimeters per mole. what does this mean? This means this has important implications in terms of reactions, because it means that for reactions at constant temperature and pressure, the gas volumes will react in the same ratio as molar ratio. And I'll show you what is it that I mean right now. So let us say we had a chemical reaction between nitrogen and oxygen to form, right? Oxygen to form NO2. So, we want to balance it first. So we say number of oxygens, the number of nitrogens as well as the number of oxygens. So this side we have 2, the other side we also have, the other side we have 1. So we must multiply this by 2. So multiply by 2 so that we can get 2 nitrogens. Okay, on this side we have 2 oxygens. On this other side we have 2 times 2, which is 4. So we have 4. To get 4 on this side, multiply by 2 again. So that is our balanced equation. So it's very important to always make sure that your equations are balanced. It's a very important thing. So if we have this type of reaction, we know that 1 mole of nitrogen reacts with O2 there, oxygen, with 2 moles of oxygen, like I said, and then it forms 2 moles of our NO2 right there, right? At STP, this at standard temperature and pressure, this means that the volume will also be in accordance to this mole ratio, right? It will also be 1 dm or cubic decimeter, which will react with 2 cubic decimeters, and then even this side will have 2 cubic decimeters, right? That is what is meant when we say that at standard temperature and pressure, the gas volumes will react in the same ratio as the molar ratio. So these are the molar ratio, and you have just written your thingy, your gas volumes, right? So it's just quite important for you to be able to know that. So let us take a quick example to kind of make sure that you actually understand what we've just spoken about, because it's important. So we have a question over here, and it says to us, what volume of oxygen at STP is needed for the complete combustion of 2 cubic centimeters, I'm lying, 2 cubic decimeters of propane. So they've also given us the balanced equation for that combustion reaction. We really did this, I think, in the previous lesson about combustion of propane. So let's write the molar ratio of this thing. So we know that 1 mole for 1 mole of propane, we will need 5 mole of oxygen, which will give us 3 moles of carbon dioxide plus maybe 4 moles of water, right? Because it's at STP, we can also say that 1 cubic decimeters will need 5 cubic decimeters, which will give us 3 cubic decimeters plus 4 cubic decimeters of water, right? Because it's at STP, and all of our this is a gas as well, right? Cool. So we can say, okay, they've given us the volume for propane, which is 2 cubic decimeters, and they want us to find the volume of oxygen. So we will say, okay, the ratio of propane C3H8 to oxygen O2 is 1:5. So for every 1 mole of propane, we need 5 moles of oxygen. And then for every one, so also this implies that for every 1 decimeter, 1 cubic decimeter, wait, I wrote the wrong thing here. So for every 1 cubic decimeters, we need 5 cubic decimeters of oxygen, right? So now if we have 2 cubic decimeters of propane, so this is the volume of V prop C3H8. If their ratio is 1:5, it means that we will also need double this. So meaning that our thing is just going to be 2 times 5, right? Which will give us 10, meaning that the volume for our oxygen will just be 10. I'm hoping that is in the short, 10 cubic decimeters. Right? I hope that is making sense. If for 1 we need 5, then for 2 we need 10, because of ratio. Their ratio is 1:5. Trying to see if we can take just one last example quickly. So let us quickly do this question. It's a very interesting question as well. So they say methane burns in oxygen, so it's a combustion reaction forming water and carbon dioxide, right? And then according to the equation that they give us here, right? And they say that if 4 cubic decimeters of methane is used, what volume of H2O is produced, right? So they've given us the volume of methane that is used up. So, and this is at STP. So we know that for 1 mole of methane, we will need 2 moles of oxygen, and that will produce 2 moles of water plus a mole of carbon dioxide. Can also write the same thing in terms of volume. So we say for every 1 cubic decimeters of methane, we will need 2 cubic decimeters of oxygen. That will give us 2 cubic decimeters of water and 1 cubic decimeter of carbon dioxide. So now it's just a matter of checking what is our ratio of methane to water. So we see that ratio of CH4, which is our methane, to H2O is 1, because there's 1 mole for 2. 1:2. So for every 1 mole, or for every 1 cubic meters, there is 2 cubic decimeters of water. This means that if then we have 4 cubic decimeters of methane, it will just be 4 times 2, which will give us 8 cubic decimeters of water. So meaning our answer is that volume will actually be 8 cubic decimeters of water will be produced. Cool. So you can see how quite straightforward it is to find these volumes when you have your balanced equations, right? Cool.